Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be continuing from the previous that I made about friction. So this is sort of the examples that go with my previous video about friction. Now that last video I cut off at about 15 minutes and sort of with the promise, at least in the description, that I would come back and work some examples for you all with friction. And so in this video, that's what I'm going to do. There's not really anything to say you need to recall this, but here are the kind of relevant equations that we ended up with. You should really be watching the other video first, the one about friction, where I walk through all these arguments. Today we're just doing some examples, 2 of them to be precise. In the first example, we have a block which has been placed on a flat, that is horizontal tabletop, and it is going to be pulled along the table with some amount of force. And so what we want to know is how much force needs to be applied to this block before it starts moving, and in the event that that much force is applied to the block continuously, so it's now moving, what will its acceleration be? To solve the first part of this question, we basically understand that for this block, as a free body diagram, we have, yes, gravity and the normal force, and those two should exactly cancel each other. So gravity is in one direction, the normal force is in the other direction, and the two have the same magnitude. On the other hand, we have this force that we're pulling with. We can call it Fp for pull, and we have in the other direction the friction force, F friction. I'm just going to use an F of a lowercase f in the subscript. In order to make the block move, the force that we're pulling with needs to exceed the maximum force of friction present. It is initially at rest, so we could say to make it move from rest. If it's already moving, then obviously we have a slightly different scenario. So in equation form, we also know that for static friction, this must be less than or equal to the normal force, which in this case is mg, times the cosine of the angle theta, all times the coefficient of static friction. So coming back over here, we're told that the coefficient of static friction is this term right here. The coefficient of kinetic friction is this term right here. And of course, this right here is the mass of the block. So plugging everything in, we basically could say something like force pull needs to be greater than mg cosine theta times mu s, and so that is 0.052 for mu s times 9.5 kilograms for m times 9.8 meters per second squared for g times the cosine of 0 degrees for that tabletop. When we plug these numbers into our calculator, we get about 4.8412 newtons. So we might say, therefore, that the pulling force needs to be greater than about 4.8 something newtons. The second part of this problem involves asking what the acceleration is, assuming that we have this much pull force. So we should be able to write that the sum of forces is the mass times the acceleration. Therefore, the pulling force minus the force of friction is the mass times the acceleration. And so what we end up having is the pulling force minus mg cosine theta times mu kinetic is equal to mass times acceleration. So mass times acceleration becomes 4.8412 newtons minus, and then mu for the K was 0.039, this number here. So minus 0.039 times mass, 9.5 kilograms, times G, 9.8 meters per second squared, times cosine 0 degrees. So basically we plug all of that into our calculator, the 0.039 times the 9.8 times the 9.5 times the cosine of 0, and we get that the net force is about 1.2103 newtons. So this net force is mass times acceleration. Therefore, acceleration is about 1.2103 newtons divided by 9.5 kilograms. So if we divide by 9.5, we end up getting 0.1274 meters per second squared. And so that ends up being your acceleration for this problem. Okay, that's the first of our two examples. Let's pop over to the second example. For this one, we're told that there is a block sliding along a horizontal surface with some known speed, and after a certain distance it comes to rest. Now, the assumption here is, of course, that there is a constant amount of friction acting on this block to slow it down. We want to know what the coefficient of kinetic friction is between the block and the surface. So if again I draw a free body diagram for this block, again there's going to be a normal force, again there's going to be gravity, and those two should cancel each other out. There is also a friction force, it's the kinetic friction force, and the block is moving in this other direction. So again, we can say that the sum of forces is the mass times the acceleration, and so that means that the kinetic friction is equal to the mass times the acceleration. Therefore, the acceleration, we need the acceleration. So need acceleration. All right, well, to get the acceleration, we use some kinematics. So we know that 2a times d is v final squared minus v initial squared. Final speed is 0. The initial speed is given as 4 meters per second. So this is v initial. Okay, that means in turn that the acceleration is negative v initial squared over 2d. So that's negative of 4 meters per second squared divided by 2 times 6 meters is the given distance, so 6.0 meters. That means that my acceleration is basically 1.3 or negative 1.3 repeating, 1.333 meters per second squared. That means that the force being applied, force of friction, was the mass times the acceleration. And again, this right here is the mass of the block, 5 kilograms. So we have 5.0 kilograms times 1.333 repeating meters per second squared. Now I could plug that into my calculator and get a value for the force of kinetic friction, but I don't, strictly speaking, need to do that. So if I do plug it into the calculator, I end up getting essentially like a 6 with a 6 repeating. So we could say 6.7, was rounded there, newtons worth of force is being applied. But with that said, we don't actually need to have done this step because we also know that the force of kinetic friction is mu times m times g times, cosine of theta. And so what that means is that we have mu kinetic, the thing we're looking for, is equal to ma divided by mg cosine theta. The two m's actually cancel, and so we're left with 1.333 meters per second squared divided by 9.8 meters per second squared times the cosine of 0 degrees. So if we divide this 1.333 by 9.8, we get mu k is 0.136054388. There's no units to that coefficient. So now we just round it off to two significant figures as per the problem, and we have mu k is 0.14. All right, so that's all for today's video. That is a couple of examples related to friction. So hopefully, having watched this video and having watched the other video, this video helps you understand what I did in the previous video a little better, and B, hopefully in general you've learned something from the two of them. Until next time, thanks for watching.